The Gross-Neveu-Yukawa (GNY) chiral Ising transition is a critical phenomenon that has been extensively studied using various methods, including conformal bootstrap, perturbative renormalization group, and quantum Monte Carlo (QMC) simulations. However, the finite size effect has hindered the convergence of critical exponents. This work addresses this issue by employing the elective-momentum ultrasize (Emus) QMC method to compute the critical exponents of the O, N, 2, squared Z GNY N equals 8 chiral Ising transition on a 2D pi flux fermion lattice model. The Emus QMC method allows for the matching of fermionic and bosonic momentum transfer and collective update in momentum space, effectively accessing larger system sizes and reducing computational cost. The results provide fully consistent exponents with those obtained from the bootstrap and perturbative approaches, including EPS equals 0.04, 2, F equals 0.72, 6, and nu equals 1.07, 12. The model consists of fermions and bosons interacting via Yukawa coupling, and the Emus QMC method is employed to simulate the linear region of the Brillouin zone, BZ, near the Dirac points. The simulation results are presented in figures 2 and 3, showing the square of the bosonic order parameter and the correlation ratio as functions of the control parameter for different system sizes. The data collapse of these quantities allows for the extraction of the critical exponents, 1, nu, f, which are consistent with previous studies. The Emus QMC method is shown to effectively reduce the finite size effect, enabling the simulation of larger system sizes with reduced computational time. The consistent results obtained in this work demonstrate the power of the Emus QMC method in exploring conformal field theories and understanding quantum phase transitions in interacting Dirac fermion systems. The study presents a comprehensive investigation of the N equals 8 chiral Ising Gross-Neveu-Yukawa (GNY) model using the elective-momentum ultrasize (Emus) quantum Monte Carlo (QMC) method. The results demonstrate robustness of the critical exponents EPS and F with increasing system size, consistent with conformal bootstrap and E-expansion predictions. The Emus QMC method combines momentum space QMC with ultrasize scaling analysis, enabling efficient simulations that consume fewer computational resources than previous studies. The authors report critical exponents that exhibit textbook-level consistency with previous QMC, E-expansion, and conformal bootstrap results. The Emus QMC method's potential is highlighted for investigating various GNY transitions, including those in graphene and twisted bilayer graphene systems. The study contributes to the understanding of GNY transitions in 2D quantum systems, with implications for nematic order, intervalley coherent and valley polarized orders, and superconductivity. The Emus QMC scheme is a variation of the conventional DQMC simulation, focusing on small patches of the Brillouin zone, BZ, significant in the infrared limit. By working in momentum space, the simulation can be performed fully on momentum space, reducing computational complexity. The fermion part of the model is block diagonalized, and the coupling term is optimized to improve efficiency. The simulation's efficiency is further enhanced by optimizing the amplitude of change in the bosonic field, using larger CQ values when the updating momentum Q is closer to gamma, and expressing the bosonic interaction in terms of Fourier components. The rest of the simulation follows the usual DQMC scheme, with the fermion weight of each bosonic configuration given by y_sigma equals det, I plus b underscore sigma, beta, 0. The study is limited to the N equals 8 chiral Ising GNY model, and further work is needed to generalize the results to other models and systems. The Emus QMC method requires further validation and testing in different contexts, with future work focusing on applying the Emus QMC method to other GNY transitions and quantum materials. The Monte Carlo simulation's acceptance rate, RF, is calculated as the square of the absolute value of the determinant of a matrix that is a function of the equal time Green's function, G. This function is defined as the expectation value of the product of fermionic operators. In the context of stochastic data collapse, the authors employ a method similar to that in references 59, 60, to collapse the order parameter data shown in Figure 2, C, and D. They fit a line to the collapsed data and evaluate the goodness of fit using the R-squared value, which is a widely used statistical measure. The R-squared value is defined as 1 minus the ratio of the sum of squared residuals to the total sum of squares. The authors use weights that decay exponentially away from the critical point to focus the fitting process on the critical regime. The data collapse procedure involves scaling the data obtained from different system sizes according to a set of critical exponents, fitting a single curve to all the points, and calculating the ratio f, which measures the variation between the rescaled data and the fitted value. A small value of f indicates that the set of exponents produces collapsed data that can be well explained by a single curve, thereby validating the exponents. This method is used to test various sets of critical exponents and determine which ones provide the best data collapse.